In the first part of Newton's first law, we talked about just sort of the idea of it. Objects at rest, objects in motion stay in motion unless there's a force that makes them change, affects their inertia and makes their motion change state. What we're going to focus on this time is it's the unbalance that makes things happen. So we're going to actually come up with a way to sort of visualize and quantify that unbalance. How we're often going to draw our forces is arrows. So like this first rocket question. There's an upward force on it represented by the yellow arrow. There's a downward force on it represented by the green arrow. If you're given those force diagrams like with these arrows, whichever one's bigger, that one's going to kind of overpower the weaker one. So in this one, the upward arrow is bigger. So in this particular case, since the upward arrow is bigger, that means there's a net force. There's an unbalance that's pointed upwards. That means it's going to accelerate upwards. So wherever the bigger force is, we call the amount of unbalance the net force, and the direction of the net force tells you the direction of the acceleration. In the second one, if we draw it so that the arrows are the same length, then it's kind of like we talked about in the last document. Whatever the upward force is, it gets canceled out by the downward force. Since they cancel each other out, we say that they're balanced. There's no net force, so there's no acceleration. The answer's there in the link, but what if I told you the rocket was accelerating downwards? What would that tell you about the two forces? If it's accelerating downwards, then the unbalance must be downwards. So the downward force must be bigger than the upward force. It's kind of tough to see, so I'll do it over here. Downward force, upward force. Often when I draw them by hand, I'll just draw a dot to represent the object and then show the arrows starting at the dot. These force diagrams, their fancy name is called free body diagrams. We draw the forces tail to tail like that just to give us an idea of which one's bigger and which way it would accelerate. They can be two-dimensional. If I give you one like this car one, the answer's typed there, but if you just looked at the diagram, the up and the down seem to cancel out, so it's not accelerating up or down, and the forward and backward seem to be the same, so it's not accelerating forward or backward either. Since the forces cancel out, the net force is zero. That means the car is not accelerating. This car could be rolling forward. It could be moving forward. It's just not accelerating forward. It's going at a constant velocity. It could even be rolling backwards. Maybe it's in reverse driving down the road. It's just not accelerating backwards. When the forces cancel out, it tells us that the state of the motion isn't changing. So if it is going at a constant speed, it's not speeding up or slowing down. Or if it's not moving, it's not going to start moving. Here's a few more for you to think about. In the first one, the way I drew it, the up and the down arrows cancel out, so it's not accelerating up or down. But that forward arrow on the car is longer, so that means its net force and its acceleration are both in that direction of the forward arrow. In the second one, if I told you you're in a car and you're going to skid to a stop. Question doesn't say anything about the car accelerating up or down. Like if it was on a trampoline or an elevator, then maybe the up or down would change. So we got an up and a down force. They got to cancel each other out because it's not accelerating up or down. And then my little hint there in driver's ed, when you skid or when you brake, you're supposed to take your foot off the gas. So there's no more forward force, but we do have a backward force. That would be the free body diagram of a car skidding to a stop. Okay, the next couple I switched back to vertical. In an elevator, I don't worry about the left and right forces. It's all about the up and the down. For that diagram, red arrow up, yellow arrow down. Which force wins the tug of war? The upward force is bigger, so it sort of overpowers the downward force. Sorry, that's kind of messy. So it's going to accelerate in the upward direction. This one here, if I tell you that a person in an elevator is going at a constant speed. In an elevator, I don't worry about the left and the right. Often when I give people this question, they goof up and they get caught up by the word upward. It doesn't matter that they're moving upward. It matters the direction of the acceleration. Since they're moving at a constant speed, that means there's no acceleration. that means no net force. The way this is worded, I'm going to assume that there's gravity, so gravity pointing straight down. If we cared from what we talked about Newton's gravity, force of gravity is always mass times the 9.8 number. If we knew the person's mass, we could even get a number for that gravity. And because it says they're moving at a constant speed, I know there's got to be an up arrow that's the same length. Just do your best to try and make them close to the same size. Mine's not perfect. I think my up arrow could be a bit longer, but if it's going at constant speed, the up and the down have to cancel each other out. There's a worksheet link there. I've created answers to go with the worksheet. There's a little blurb here. The last little thing I'm going to do before we leave these free body diagrams and unbalanced forces, net stuff, net force stuff, is to remember that forces are vectors, so we can add them numerically, just like we added our other vectors, our velocities and our displacements. Sometimes 250 add up to 150 if they're in opposite directions. Sometimes 10 and 8, when they're in opposite directions, they wouldn't add to 18, they would only add till 2. Similarly, with forces, let's say I told you there's a force to the right with a value of 10 and a force to the left with a value of 8. I think intuitively, if you're pushed to the right with a force of 8 and you're pulled back to the left with a force, sorry, I said that wrong, pushed to the right with a force of 10 and pulled to the left with a force of 8, those are going to combine. The 10 and the 8 combine to make only a 2 because they're in opposite directions. So the last little thing, what if I gave you these two? What if we've got a toy rocket, the upward force on it is 100 and the downward force on it is 30. Sometimes when I write it out, I say something like F net, and in this case I would say it's the up, take away the down. Or what I should really probably do is say it's the vector up plus the vector down. The up is 100, then we add to it the opposite direction 30, so that turns into plus negative 30, which is of course just 100 minus 30, which means 70. So I'm not too worked up about notation, but you should see that the 100 and the 30 in this case, they combine to make a 70. Before I doodle it, you look at the next one. We got 800 up and 800 down. What happens to those two? Then we've got 500 forward and 100 backwards. So the net force is the forward as a vector plus the backward as a vector. Then we take into account our signs. I'm always going to make the bigger one the positive one. So I'm going to say the forward is going to be positive 500. To that we add the backward. It's the opposite direction, so it's negative 100. That of course turns into a subtraction, so our F net is 400. Its units are newtons, and I should be more thorough. This needs to have a direction, so I would say this one is to the right. And I'm going to backtrack. I should have done on that other one as well. The 70 was pointing upward. That's all that there is to this F net stuff. I think it's a little intuitive. There is a little bit of math, but it's just adding and subtracting. I've got another worksheet for you to practice with answers, and this document's out of date. Technically, this is check-in 2-3. All right, good luck with net forces and calculating net forces.